Okay, so this is a new thing that we want to try in our research group and hopefully also in other research group at macromolecular chemistry in the University of Bayreuth, which is that when I was an undergrad student and still, I really enjoyed watching videos about research and then maybe later reading about it. Also because the person who has actually done the work can give you some more detailed insight into how the project actually planned out. And this is the idea behind this. So if you're interested in our research, please watch these videos to get an initial guess. I will try to explain this as much as possible, not to the specialist in the field, but much rather to potential students, may it be bachelor's, master's, PhD, so you can get a bit of an insight into what is happening in our research group. So I picked this paper, which is called Lithium Achieves Sequence Selective Ring Opening Terpolymerisation of Tertiary Monomer Mixture. And this was more or less the last big project. There were a small project afterwards, which I did the experimental work for. So I can give you first-hand insight in what I was thinking with the experiments, how I analyzed them, and what might have not gone as much as I hoped it. So the motivation came from some previous paper by Werner, reported in Macromolecules, where they took carbon disulfide and an epoxide, propylene oxide or butylene oxide, and took a lithium catalyst. This in their case was just a lithium alkoxide, and they tried to copolymerize this. Knowing the field, what you might expect is like you form a one-to-one polymer between these two monomers. So the repeat unit of the polymer should have one oxygen and two sulfurs. Yeah, I mean, it seems like a reasonable baseline assumption. If in these called ring opening copolymerization, the monomers get enchained one after each other. This is a type of copolymerization. The assumption was, well, it should be one oxygen and two sulfurs in the repeat unit. However, what they found, instead of like one oxygen, two sulfur, one oxygen, two sulfur, is that they, in 92% selectivity, formed this repeat unit here with two oxygens and one sulfurs followed by three sulfurs. So in effect, this oxygen here and that sulfur here switched places in the mechanism. The molecular weights they reached, they were quite good. I think they reached 90 to 100,000 around that time. The dispersities were okayish, I think 1.7, you have to check. And they rationalized this by the following mechanism. So you start from a lithium alkoxide, you would add this. You would just add 1 mole percent, 0.1 mole percent of lithium tert-butoxide starter that inserts into carbon disulfide, forming such a dithiocarbonate, which then inserts into your epoxide, and to form an alkoxide, lithium alkoxide, next to this dithiocarbonate link. And now the trick was, instead of this then inserting another CS2 molecule to form this type of sequence, it was biting back. This was an unproven assumption by them. It was biting back here to form a 5-membered cyclic intermediate that then rearranged, eliminating a sulfide to form this lithium sulfide intermediate. And you see in this OS exchange reaction, as we call them, the oxygen and the sulfur here switched places. And then you insert CS2, form the lithium trithiocarbonate chain, and insert propylene oxide to close the cycle, right? And this is how they explained this. There was also like a side product that they observed, which is when this 5-membered ring doesn't open on this side, but rather kicks out the alkoxide here, you end up with a small molecule, cyclic dithiocarbonate, which you will see in one of the following slides. So what is also relevant to the study was this other paper here, where they took a so-called thioanhydride with also propylene oxide, so where R is a methyl group. And depending on the catalyst, this works better, worse or better. Like sometimes you get some errors in, but there were catalysts for which you form this alternating copolymer, right? So in effect, this here now in red is the ring open cyclic anhydride forming this thioester bond here, and then the blue oxygen and the rest of the organic part here comes from the epoxide that is being ring opened. And when I started independently in the lab, I did a postdoc before in a research group which were doing these copolymerizations exclusively with oxygenated monomers. And so CO2 and not thioanhydrides but anhydrides. And there was a paper from 2004, 2006, does it say it here? No. From the Coates group, which mixed an epoxide, now it is cyclohexene oxide, with CO2 and again like such a cyclic anhydride and this somewhat optimized like zinc catalyst here. And the copolymerization of this anhydride and the epoxide would give you a polyester like here, and the copolymerization of the epoxide and CO2 would give you a polycarbonate like here. But what they were doing is they were mixing all three monomers at the same time to see what happens, because maybe what you'd expect is that there would be some random structure in the polymer, right? You'd get some ester bonds and some carbonate bonds which have random order within the polymer chain. But or what else you could do is maybe also get some homopropagation of this, so where this exclusively is polymerizing, that would form ether links. Yeah. But what they found is when you mix all these three monomers with this zinc catalyst, you form a block polymer. So what happens first is that polyester forms from the DGA here and the CHO, this is supplied in excess. And then once all the cyclic anhydride is consumed, the copolymerization of the CO2 with the epoxide occurs. That really only starts once this is consumed. Yeah, it has to do with the fact that the alkoxide intermediate that originates from ring opening the epoxide here inserts much orders of magnitude faster into the anhydride here than into CO2. And in that way, you got this block polymer selectively from a mixture. So usually how you would make block polymers is like in living polymerizations. So in one where the chains grow regularly, so to say, and initiation is fast with respect to propagation, that you'd first just have a mixture of these two, let them polymerize, and then only once this is consumed, you'd add the CO2. Yeah, so you'd only pressure it with CO2 once the anhydride is consumed. That would be a traditional way to make a block copolymer, but the Coates group, like 15 years ago or so on, well, you can also just mix those three, and by pre-rate determining selectivity, you form this block polymer. Yeah? And then afterwards, there have been many, many papers which found this to be true for slightly different anhydrides and slightly different epoxides and different catalysts, but this really started it. So I was wondering, well, how does this work with sulfurated polymers? I was wondering, if you now take the epoxide, the thioanhydride and the CS2, and you mix all three of them, what happens? Yeah, do you also get this block polymerization? And this was really just curiosity. Yeah, I expected like either a block polymer to form or like a random polymer where maybe this repeat unit here or this structure sits like randomly with that structure. Yeah. And I just mixed them and wanted to see what happened. Yeah. And it was by sheer coincidence that a completely new structure formed. Yeah. So I termed that ring opening terpolymerisation. But essentially it's just two ring opening copolymerizations combined, where you add the cyclic thione hydride, the CS2 and epoxide, and the oxygens and the sulfurs they sort. Yeah? So you generate these diester units which alternate with trithiocarbonate units. Yeah? And the trithiocarbonate units here, they are next to CH2 groups, and the esters, they are next to the substituents here. Yeah, we also call this we call this a head-to-head, tail-to-tail selectivity, which I will explain more further. But it essentially originates from the fact that the epoxide is always selectively ring opened or nucleophilically attacked at the less hindered CH2 position. Okay, so let's go. How did this look? Sorry. So I took the monomer combination at the 1:5:10 ratio. This would go into hundreds and thousands of equivalents with respect to lithium, so as low as 0.2 mole% of the lithium alkoxide. And here you could either use lithium alkoxides or lithium HNDS. Both worked. So both alkoxides and HNDS initiated the polymerization. To form the structure, I remember mixing it, and then you got a viscous mixture that is soluble in dichloromethane, and you can precipitate it in methanol, and then the NMR spectrum of the polymer looked like this. And it was immediately obvious that this is not a block or a random polymer, because of the very symmetric aromatic region here, which really originates from a symmetrically substituted aromatic unit in the polymer backbone. So this could not be like a link which on one side has an ester and on the other side has a thioester, right? This would not have two signals. Yeah, it had to be symmetrically substituted. And well, so from the sheer symmetry of the spectrum, it was already clear, oh, this is not a random polymer, unlike even a block polymer. This is something more symmetric. And then in the carbon spectrum and in the HMBC that correlated the hydrogen spectrum to the carbonyl resonances here, it became very clear that you got this distinct correlation and signal in the 13 carbon spectrum at 166 ppm very cleanly, which correlates to the ester, and another resonance at 222 ppm, which correlated to the trithiocarbonate, and the CH2 groups here correlated to the trithiocarbonate, whereas the aromatic units as well as the CH groups from this tertiary center here correlated to the ester. So that was relatively clear. Also, like, the polymers are yellow. I think they have glass transition temperatures around 30 degrees. You can press them, so they are thermoplastics, you can press them into films. They are yellow because of this carbon-sulfur double bond, which is a chromophore. So this polymerization was not perfect. The 1H spectrum looked very nice, but you can already see there are some small signals here, and there seems to be something here, and there's something here. So there were some other signals in the spectrum. And then in the carbon spectrum, this really came out that there were some errors which occur from just copolymerization of the anhydride with the epoxide. So this ester thioester repeat unit that you get just from the copolymerization of the cyclic thioanhydride and the epoxide, right? And you could see this quite clearly because 13 carbon spectrum really helped us out here, because the ester, thioester, trithiocarbonates, all of these carbonyl resonances, they spread over 60, 70 ppm, and they come very definitively. So within 2 to 3 ppm, regardless which substitution they have, they can really be used like a fingerprint. And so something that comes around 192, 193 ppm in the carbon spectrum, that's usually a thioester. And it was clear, well, these seem to be errors in this sequence. Okay, so just to repeat, this was the structure that we formed, which formed in a so-called head-to-head, tail-to-tail selectivity. So the CH2 is, people term the tail position of the epoxide, and the CH with the substituent, people term the head position of the epoxide. And the ester were always next to CH positions, and the trithiocarbonates were always next to CH2 positions. You got some of these errors here, which occur when just the copolymerization of the epoxide with the thioanhydride occurs, but you did not observe any errors from when just the CS2 copolymerized with the epoxides. Instead, what you also formed in some as a minor byproduct that can be easily purified by precipitation was this cyclic dithiocarbonate, which is from an elimination pathway that we will look at later. So the proposed mechanism of this was that you add some sort of alkoxide, and the alkoxide inserts the thioanhydride and then forms a thiocarboxylate intermediate. That then inserts into the epoxide here at the CH2 position, forms an alkoxide next to a thioester unit, and then backbites in here, forms the cyclic 5-membered intermediate that then collapses to form you a thiolate, a lithium thiolate, next to an ester, which then, well, and this is like an OS exchange reaction, like in the original report from Werner that I discussed in the introduction of this. Then the thiolate had to insert CS2. This is at the current point just a hypothesis, yeah, to explain the sequence. Then the sulfur had to insert CS2 to make a lithium trithiocarbonate, which then inserted the epoxide to regenerate the alkoxide, which is explaining the cycle and the sequence. So what I thought at the time these errors are originating from are like when the alkoxide next to the thioester then does not do this rearrangement and inserts the cyclic thioanhydride. Yeah, and by that you have some thioester errors in the sequence. Alternatively, when the thiolate after the rearrangement does not insert CS2 to form the trithiocarbonate, it inserts PTA to form thioester bonds, right? Because from the you can now dial back and look at the carbon spectrum again, and there you see there were some thioesters in there. Yeah, so I had to formulate some hypothesis how where these originate from, so to say. Then there was this other byproduct, the cyclic dithiocarbonate, and this comes from, for example, yeah, when the lithium alkoxide, instead of propagating, bites back. Yeah, so this attacks now here, forms another 5-membered intermediate, and that then eliminates here the thiolate to form the dithiocarbonate. Yeah, this is one pathway. Yeah, the other pathway would be when an alkoxide next to a thioester would insert CS2, then propagate and then eliminate, by essentially the same pathway. Okay, so after I discovered that this monomer combination would form the sequence, and I had some picture in my head how I think that the different links form, I went to investigate how the different loadings, so ratios of like lithium catalyst to epoxide to CS2 to thioanhydride would influence the selectivities. And this is somewhat expected to do this in this field that we are working in, to get some understanding of the catalysis. And what was immediately apparent, right, up on, these are the monomers, right, this is the initiator, up on throwing more and more monomers per initiator, right, the molecular weight increased with the maximum that I could achieve of 11 kilograms per mole. The polymer selectivity with regards to the small molecule stayed approximately the same, but the linkage selectivity went somewhat down. And I defined here linkage selectivity of this new ester trithiocarbonate alternating sequence to thioester linkages. This is how I defined it. You can also define it in different way. But what was like relatively nice is that we could reach like high molecular weights of 110. This is not always the case. Like we then showed otherwise for such sequence selective polymerizations that you decrease the loading. So like, I mean, if you have some sort of controlled or living polymerization, you'd expect that if one initiator, like so the alkoxide, enchains more and more monomers by like having more monomers per initiator, that you form longer and longer chains, right? That would be the baseline assumption, but this is not always the case in reality due to side reactions other than the ones that I showed you. But the dispersities, even for these types of polymers, were like not the worst, but somewhat broad. And we didn't investigate in this study why this was the case. But it is something to point out. Just to remind myself here, H was, I think, with potassium. Yeah, there you go. So with sodium, instead of lithium, it was slower, and the linkage selectivity was lower. And with potassium instead of lithium, it did not work at all. Which might be somewhat surprising. So from that, we concluded that the lithium might actually play some active role, like in the polymerization that we investigated then afterwards further. Rather than, like just having like some anionic chain and that propagates and the lithium being desolvated apart from the chain, and like we thought, I did this mostly myself, that it would stay attached and have some sort of role that we then afterwards investigated further. When you had no PTA and you did it at 80 degrees, that was the temperature that I conducted the polymerizations at. It was a bit trial and error, like which temperature I took. Like lower temperature worked, but they were relatively slow. And for higher temperatures, because CS2 and PO were so high boiling, I was always a bit worried that my reaction vessel would leak. 80 degrees is already over the boiling point of CS2 and PO. But it remained stable, but like at much higher temperatures, sometimes it leaked, just due to the pressure that was building up. So that's why I stick with 80 degrees. And at 80 degrees, if you don't have any cyclic anhydride, thioanhydride present, yeah, you do not form any polymer. You just form the cyclic dithiocarbonate, no polymer, yeah, which means that like the terpolymerisation really did improve the polymer selectivity of the process a bit. Okay, then because we observed the alkali metal had some effect on the catalysis, right? Because with potassium it did not work at all. I went to study some model intermediates, some species that I thought would form during the catalysis, to study their reactivity, which I hoped would help me understand what is special about lithium. And so we had good reason to believe at the time already that the slowest step of the reaction was after the chain end inserted the cyclic thione hydride to form this lithium dithiocarbonate. And the insertion of the epoxide by such a species was likely the slowest step of the polymerization. This was relatively clear because when you the copolymerization of CS2 and epoxide was much faster than the copolymerization of PTA and the cyclic thione hydride and epoxide. So from that it was relatively clear that likely the insertion of the epoxide, but this is the slowest step. So I went to study such an intermediate synthetically. So what I did, I just mixed stoichiometrically lithium terbutoxide and the cyclic thione hydride PTA, and formed this salt. It's just ring opened thione hydride with here's the original alkoxide. And I crystallized it, get a crystal structure to see how the lithium is bonded to it. Of course, this is a crystal structure, right? So it's not a solid state, so you never know how it's actually looking in solution. And also not only how it's looking at solution, but if it can transform into a less stable species in solution, but that then is more catalytically active. So you have to be cautious with looking at crystal structures as solution state structure or catalytically active species, but you can make some modest assumptions. This is how it crystallized. It formed this nice dimer, where importantly the lithium is not coordinated by the sulfur, and the sulfur sticks out. It's already nice, and we crystallized it from tetrahydrofurane as a model for epoxides. You cannot crystallize it from epoxides; they would just react with it. So I used THF, and it forms this nice dimeric arrangement, right? So now I took this species, powder stoichiometric reaction, reacted it with epoxide, and what you can identify is are these thioranes forming and the carboxylates forming. So this more or less proved this rearrangement reaction. How does this rearrangement happen? Or how do these species likely form? It's by the oxygen ring opening the epoxide. Then again, you have an alkoxide next to a thioester that then exchanges to a thiolate next to an ester, and this then eliminates the thiorane. But essentially, the sulfur gets shuffled from an epoxide into a thiorane. That then proved well. This exchange seemed to be also reproducible in small molecule reactions and seemed likely. When you did this not stoichiometrically with epoxide but with an excess, you could then actually see that this rearrangement, right, and the epoxide inserted here, and it rearranged to form an ester, right? Although you had a sulfur initially at the aromatic unit, but when you reacted this species with an excess of epoxides, you only formed esters, which kind of confirms this exchange reactivity of the species after epoxide insertion by the trithiocarbonate, and then similar things were observed when you had some CS2 present. But what was perhaps more interesting is that when you made this species, yeah, with potassium and sodium, yeah, these are now softer metals, and the crystal structures then showed that the sulfur also coordinated to the sodium or to the potassium, right? In lithium, the sulfur is nice and free and coordinated, and so to say ready to then attack a new monomer and propagate, right? Whereas for sodium and potassium, right, you got some network structures that crystallized out. And I mean, it's a reasonable hypothesis that when you move to softer alkaline metals, yeah, they start coordinating the sulfur. And so my hypothesis at the time was like that means that the sulfur is maybe less more encumbered to propagate for heavier alkali metals, which makes the catalysis slower or deactivates the polymerization altogether. Yeah. This was the hypothesis, right? I mean, we did not go on and study this with density functional BOT. It's as good as it got at the time. Then what I eventually did, right, because this still seemed to be a reasonably controlled polymerization, is making a block polymer. So this is a concept that is called switchable catalysis. I did not invent this. Where what you can do is you can polymerize a lactone, right? This is a cyclic ester, and you can do a ring opening polymerization to a polyester with this. And you can use epoxide as a solvent here. Yeah. And with lithium alkoxide initiator, so this really only works when X is an alkoxide like benzene. I think I used lithium benzyl oxide. And what happens is that you do ring opening polymerization of the lactone, here in this case epsilon decalactone. Why did I use epsilon decalactone? Because it was very established for this type of catalysis, and it gave good control, nice dispersities. I think didn't try this with lactite and lithium salts, but lactite is intrinsically, there's work from Weymouth showing that you then need more complex catalysts, not super complex, but the polymerization you're just using lithium salts and epsilon decalactone. This was reasonably controlled, so I went with it. And you can do this in epoxides without any of the epoxide polymerizing. Yeah, this works very well up until you add the carbon disulfide and the PTA, yeah, the cyclic thione hydride. And what then happens is the polymerization of the green monomer of the lactone stops altogether, and you form this terpolymer block here. And so again, this ester trithiocarbonate unit, repeat unit attached to it, and all the lactone that was residual and that was unconsumed at the ring opening polymerization step remained in there, yeah, and didn't consume further. Right? This has to do with the fact that alkoxide intermediates, yeah, which are able to attack lactones, they insert either CS2 or the PTA again much faster than they would insert the lactone. So any alkoxide intermediates after you've added these monomers are scavenged, yeah, and are too short-lived or like to achieve the polymerization of this further. Yeah, and this was the concept that was in the literature, and I now use this for this new terpolymerization. Here's some aliquot monitoring of the reaction mixture. Where does it start? Here, here it started. Here in the beginning, you see the monomer, the lactone, and the polydecalactone. Then, as the polymerization progresses, this gets a bit less intense, and this gets a bit more intense. I had to add some acid, right, just to quench it to get an NMR, right? Otherwise, you take an aliquot and the polymerization continues in the NMR tube, so you have to usually add something to make it stop. And and then even further, I added the PTA and the CS2, and you could see there's still some unconsumed epsilon decalactone here present. But as now, after the addition of the sulfurated monomers, the sulfurated terpolymer grows and grows and grows, right? And the cyclic thioanhydride is consumed. Yeah, this trace of lactone here stays in the reaction mixture, right? And then the block polymer, again, you purify it by precipitation, and you could analyze it by NMR, really seeing that there also is no cross propagation, right? So you have no links which consist where you have a random lactone unit inserted in the terpolymer sequence or so. Yeah, the NMRs were very clean. Here are the GPCs, right? So this is the GPC after the ROP stage of the lactone, and this is the GPC after the sulfurated rho-terp stage. And it grows nicely. Then of the isolated block polymer, you could really see like a stepwise decomposition for the sulfurated block starting to decompose about 200 degrees and the lactone block starting to decompose about 300 degrees. And in the glass transition temperature, they phase separated. We could then later also see this by AFM and by SAX. But here just DSC showed us two glass transition temperatures, which around 30-ish degrees, which we determined before for just the isolated terpolymer, that this was really that this was expected, that the block would be here, and then for epsilon decalactone, polyepsilon decalactone, it was known that it's around minus 50 degrees. Yeah, you see that they move a bit to each other, right? So which is typical for block polymers, because they do mix a bit and then plasticize each other a bit, that they don't phase separate perfectly. And then in the NMR, you could like also assign each of the signals like relatively cleanly, and there was no weird signals, perhaps from like, you know, where you like not, so the structure that formed was a nice block of this and a good nice block of this like followed, and there were no extra signals for where like such a unit would be randomly would have random ester polyepsilon decalactone ester units squeezed in there, yeah, from wrong propagation steps. Okay. This brings me to the end of the paper. It took me 37 minutes. What would I do different now? So this was my first paper when I was independent. And you already see that this was quite complicated. And this for the presentation, I cut it down. So I did some more model reactivity studies with the sodium salt and the potassium salt that I showed you before. And in my initial submission, of this paper, I had even more block polymers in there. So this was way too complicated. Like this was my first paper, and I was like, oh, I want to show everything in the same paper and to make a great paper. But it just got overly complicated. And all the referees also said like, it's too complicated, yeah, cut it down, and the block polymerization, don't like make it in another, report it in another paper, and do the mechanism more in detail. Of course, like you got different opinions, but this was the overall response that I got from the reviewers. So I would probably in the future try and make the story better, right? So instead of having this block polymer and this block polymer sequence part in the end, and also this with the different alkali metals, I'm not sure to what degree it was necessary, and would have been nicer to really show the mechanism much more cleanly rather than just some wild hypotheses that I had, which I mean they made sense, and we had a follow-up paper that then showed they make sense by density functional theory and by reaction kinetics and more model intermediate studies. And rather than having that in the follow-up paper, I would probably now just discuss the sequence, because the sequence was new, that 3 of these types of monomers form this new sequence. This was actually quite exciting, which also the reviewers pointed out. And then really do an in-detail mechanistic study understanding how the sequence came together, which we actually have a follow-up paper in Catalysis Science and Technologies the year following. Check it out on our website. It was with Peter Degelman as the first author, who did a miraculous job on the DFT. I'd probably do that, right? To cleanly present, this is a new sequence, this is how it forms, these are the reasons for it. Because there are a number of selection processes that need to go right, yeah? This was the exciting part. But much rather with like doing the different alkali metals and the block polymers in the same paper, I overcomplicated it, I think. And this got into ChemSci, which is good, yeah? But it got desk rejected from Angewandte, which, I mean, I think part of this was because it was that did not have like a very clear message, and they tried to do everything in the same paper. Okay, please let me know in the comments what I should do better in the future. Some improvements that we could do. And feel free to reach out to me and ask me questions about the work. The idea would be that in the future, the PhD students and master and bachelor students who did the work would do these types of presentation. I'm trying to set an example here. See you back soon at our hopefully new YouTube channel.